This lab will use Newton's second law to predict the future position of a system in motion. Specifically in this instance, the motion is constant as we assume the net forces will be equal to zero. As you can see from the video, my observed experiment uses a frisbee in flight. We captured the frisbee shortly after release and prior to the flight path starting to descend in order to study the segment of the flight under the assumption that the net forces are zero. During the period of flight, we assume several things. One, that the lift force is equal to the gravitational force, which implies that it will be a flat flight path. Also, we assume that the acceleration is at zero and that the drag force is at zero. In essence, constant velocity. One other assumption we make is that the distance from the camera is relatively constant. In other words, the angle of observation doesn't alter the perceived velocity. Additionally, I had to mark specific points along the flight path in order to be able to collect the data needed for this experiment. So what I did is each frame step passed, I marked the position of the frisbee on the display. Also, I had to make sure that the coordinate reference was proper. So I laid the coordinates out, putting the origin at the zero position of the frisbee, and I needed to tilt the axis. I've also oriented the axes so that y positive is up, x positive to the right. So in my example here, my x values will be negative. In order to create a computational model of this system, I took the Python program, Lab1 start, and modified it to fit my system. I needed to get the diameter of the frisbee, referenced as ball in this code, and transferred the value from the video, the 2.667 e to the minus 1, into the variable as 0.2667. I also needed to get the average velocity, and my value came out to be minus 4.259 meters per second. I transferred that value, minus 4.259 meters per second, to that initial variable. Additionally, I set the initial position to 0, which corresponds to my visual graph, and also set the time equals 0, which is the starting point. With these initial variables set up in the Python program and the delta t, the change in time, set to 1/100th of a second, I run the program and get these results. You can also see that once the data from the model and from the experiment are transferred to a spreadsheet and graphed in a line chart, that the line chart of the model position very closely matches the graph output from the Python program. That just helps to validate that the data transfer between the two programs into the spreadsheet seems to be valid. The model predicts pretty well what was observed in the experimental case. You can see some discrepancy in the middle of the graph of the experimental model, indicating that the velocity did indeed increase and then decrease towards the end. In our experiment, where on either end those angles do give a perception of a smaller distance being traveled over the same amount of time, would account for a smaller velocity or a greater velocity viewed in the middle of the flight than it would at either end. So based on the correlation between the observed data and the experimental data, computational data, it appears that Newton's second law, assuming that net forces are equal to zero, does do a very good job of plotting a future position